Hello students, myself XII-Sci Gorane from RBNB College Srirampur. We have already studied chapter from 12th science, that is wave optics. Now today we solve some numericals based on this chapter. First numerical is, in Young's experiment, the ratio of intensity at maximum and minimum, the ratio of intensities at maxima and minima is, ratio of intensities is given in interference pattern is 36:9. What will be the ratio of intensities of two interfering waves? Two interfering waves. Ratio of intensity at maxima and minima is given. So given is I maximum to the I minimum, and this ratio is 36/9, that is 36:9, and we have to find the ratio of intensities of two interfering waves, that is we have to find I1/I2. This ratio we have to find. Now we know I max upon I minimum is A1 plus A2 its square divided by A1 minus A2 its square. A1 plus A2 square upon A1 minus A2 square, and this ratio is given, and that is 36:9. It means this A1 plus A2, taking the square root, we get this is 36:9, that is 6:3, 6:3. That is 2:1. A1 plus A2 upon A1 minus A2 is 2:1. Now by componendo and dividendo, we write this as A1 plus A2 plus this A1 minus A2 divided by this minus this, that is A1 plus A2 minus A1 plus A2, that is 2 plus 1 upon 2 minus 1. A upon B is equal to C upon D, then A plus B upon A minus B is equal to C plus D upon C minus D. By that ratio, A2 becomes 0. 2A1 upon 2A2 is 3:1. It means A1 upon A2 is 3:1. By solving this, we get A1 upon A2 as 3:1. Now we have to find the intensity ratio, that is I1 upon I2. A1 square upon A2 square, or we write this as A1 upon A2 its square. That is 9. So this intensity ratio is 9:1, or we write it as I1:I2 is, that is equal to 9:1. So this is the intensity ratio. Very simple part. Now we see next numerical. A double slit arrangement produces interference fringes for sodium light having wavelength lambda 589 nanometer. Lambda is 589 nanometer, that are 0.20 degree apart. .20 degree apart. What is angular fringe separation? We have to find the angular fringe separation if entire arrangement is immersed in water. Of refractive index 1.33. Refractive index of that water is given and it is 1.33. Firstly, see the given data. Lambda is 589 nanometer, that is 589 into 10 raised to minus 3 meter, 9 meter. We know this is wavelength. Then theta is given 0.20 degree. Refractive index is given 1.33. A is the slit width. If A is slit width, we have to find angular separation when arrangement is dipped in water. So we have to find theta dash when dipped in water. Initial theta is 0.20 degree. We have to find theta dash when dipped in water. We know theta is lambda upon A. We know this formula. Theta is equal to lambda upon A. Therefore, 0.20, theta is 0.20 degree, and that is equal to lambda upon A. Therefore, lambda is 0.28. Actually, this lambda is given here, but see here we just write these values 0.20 lambda upon A. Hence, lambda is 0.20A. Now, when it is dipped in water, the new wavelength lambda dash is lambda upon A, n. When dipped in water, new wavelength lambda dash is equal to lambda upon n, and that lambda from this equation it is 0.20A. So this lambda dash is 0.20A upon n, that is 1.33, or for simplicity we write it as 0.20A. This is nothing but 4 by 3, or we write it as 3 by 4. 4 upon 3 means 3 by 4. So this lambda dash is 3 by 4 into 0.28 for our simplicity. This is 0.05, 0.15A. lambda dash is, this is 0.05, lambda dash is 0.15a. We get value of lambda dash as 0.15a. Now our new theta dash that we have to find, that is lambda dash upon a. But what is our lambda dash? That is 0.15a divided by a. Hence our theta dash, new angular separation will be 0.15 degree. Actually this lambda is given here, but we write simply it as lambda, and substituting in that value we find lambda dash, new wavelength, and new angular separation will be lambda dash 0.15a upon a, and we get theta dash as 0.15 degree. Very simple numerical. See next one. In biprism experiments, the fringes are observed in the focal plane of eyepiece. At a distance of 1.2 meter from slits. The distance between the central bright band central bright band and 20th bright band is 0.4 centimeter. When convex lens is placed between biprism and eyepiece, biprism and eyepiece, 90 centimeter from eyepiece, the distance between two virtual magnified images is found to be 0.9 cm. (0.9 centimeter). Determine wavelength of light used. Wavelength of light used. That is, we have to find the lambda. Biprism experiment is there. We know fringes are observed in the biprism experiment in the focal plane of eyepiece at a distance of 0.2 meter from the slits, and distance of 20th bright band is given, and that is 0.4 centimeter. Now from this our given data is, see the data, Y20
Thank you.
that is 0.4 cm. 0.4 into 10 raised to minus 2 meter. Then capital D, that is 1.2 meter. Capital D is 1.2 meter. Number of fringes n are 20. So n is 20. Why 20 is given? N is given. And we have to find the wavelength of light used. Then D1 is given, and that is 0.9 cm. Virtual magnified images, distance between virtual magnified images is given, D1, that is 0.9 cm. 0.9 cm, 0.9 into 10 raised to minus 2 meter. Distance between virtual magnified images, D1 is given, 0.9 cm. Then V is 90 centimeter. See here. When convex lens is placed between biprism and eyepiece, 90 centimeter from eyepiece, then V is 90 centimeter. V is image distance 90 centimeter, that is 0.9 meter. We write it as 0.9 meter. Now image distance U is that capital D upon V, D minus V, 1.2 minus 0.9. So this U is 0.3 meter. U is 0.3 meter. We have to find lambda. To find the lambda, we firstly find small d, and we know d1 upon d is equal to V upon U. Image distance, object distance, distance between the slits, d1 is distance between the magnified images. We have to find small d. So this small d is d1 U upon V. d1 into U upon V. What is d1? That is 0.9 into 10 raised to minus 2 meter. U 0.3. V, that is 0.9, and clearly that D is 0.9 get cancelled, D is 0.3 into 10 raised to minus 2 meter. Now distance between the 20th bright band Yn is given, and that Yn we know n lambda capital D upon D. Yn is n lambda capital D upon D, and hence this Yn is lambda is Yn into D upon n into capital D. Yn into D upon n into capital D. Now we simply substitute the values here. If we substitute the values, we get lambda. Yn, that is Y20 is given, that is 0.4 into 10 raised to minus 2. D is given, small d we already obtained, that is 0.3 into 10 raised to minus 2. Divided by n is 20 into 1.2. 20 into 1.2. See here, 0.12 into 10 raised to minus 4. Lambda is 0.12 into 10 raised to minus 4 divided by 20 into 1.2. 20 into 1.2. So this is 1.2 into 10 raised to minus 5. Upon 1.2 into 20, 1.2 get cancelled, and that 1 by 20 is 0.05. This 1.2 get cancelled, lambda is 1 by 20 is 0.05 into 10 raised to minus 5 meter, or we write it as 5000 into 10 raised to minus 10 meter, or hence this lambda is 5000 angstrom unit. Very simple calculations. Lambda is 5000 angstrom unit. Now we see the last numerical based on this chapter. Just write the formula. For the correct formula you will get half mark, correct substitution half mark, then correct answer with unit 1 mark. Just write the correct formula, you will get half. See last numerical. Monochromatic electromagnetic radiation from distant source passes through slit. Source passes through slit. The diffraction pattern is observed on a screen . 2.50 meter from slit. If width of central maximum is 6 mm, width of the central maximum is 6 millimeter. What is slit width if wavelength is given for 3 cases. For first case, the wavelength is 500 nanometer. That is the visible light. This is visible light. We have to find the slit width for this visible light, 500 nanometer. Second is 50 micrometer, that is the infrared radiation. And third, we have to find the slit width for 0.500 nanometer, that is for the X-rays. Monochromatic electromagnetic radiation from the distant source passes through the slit. Diffraction pattern is observed on the screen 2.50 meter from the slit. So capital D is 2.50 meter. 2.50 meter from the slit. Slit width of the central maxima, we call it as WC. Width of the central maxima is given, that is 6 mm. We write it as 6 into 10 raised to minus 3 meter. 6 mm. We have given 3 wavelengths, lambda 1 that is 500 nanometer, that is 500 into 10 raised to minus 9 meter. Second wavelength we call it as lambda 2, that is 50 micrometer, 50 into 10 raised to minus 6 meter, micro to meter minus 6. And again lambda 3 is 0.500 nanometer, that is 0.500 into 10 raised to minus 9 meter. We have to find width of the central maxima. What is the width of the slit width for these wavelengths, and width of the central maxima is given, that is 6 mm. We have to find slit width. That is A, we have to find. Now see what is the proper formula for this. Width of the central maxima, WC. We know the formula for width of the central maxima as 2 lambda capital D upon A. Therefore, this slit width A is 2 lambda capital D upon width of the central maxima. 2 lambda capital D upon width of the central maxima. Now see first case. In first case, this lambda is 500 nanometer. We see one by one. For first case, lambda 1 is 500 into 10 raised to minus 9 meter. 500 into 10 raised to minus 9 meter. We substitute here values 2. So A is, in first case, this A is 2. Lambda is 500 into 10 raised to minus 9. Capital D is 2.50. That is 2.5. Upon this, width of the central maxima is 6 into 10 raised to minus 3. See here, 500 into 2 is 1000, that is 10 raised to plus 3. 10 raised to minus 9, 10 raised to minus 6. So numerator is 2.5 into 10 raised to minus 6 divided by 6 into 10 raised to minus 3. 2.5 into 10 raised to minus 6 divided by 6 into 10 raised to minus 3. We have to just solve this part. So A is 2.5 upon 6. Simple calculation, that is 0.4167. Minus 3 when shifted to numerator becomes plus 3. Minus 6 plus 3, 10 raised to minus 3. So this A is 0.4167 into 10 raised to minus 3 meter. 0.4167 into 10 raised to minus 3 meter, or it is 0.4167 mm. This is for the first case. Now for the second case, lambda 2 is, we solve the second part now. Here lambda 2 is 50 into 10 raised to minus 6 meter. This value is 50 into 10 raised to minus 6 meter. Again the same formula, slit width 2, A is equal to 2, lambda is 50 into 10 raised to minus 6. Capital D, we already know it is 2.5 divided by width of the central maxima 6 into 10 raised to minus 3. 50 into 2 is 100, that is 10 raised to plus 2, minus 6, 10 raised to minus 4. So this is 2.5 into 10 raised to minus 4 divided by 6 into 10 raised to minus 3. 2.5, 6 into 10 raised to minus 3. Now we know this part, 2.5 upon 6, that is 0.4167. Minus 4 plus 3, 10 raised to minus 1. This is in meter. 0.4167 into 10 raised to minus 1 meter, or we write it as 41.67 by rearranging the decimal point minus 3 meter. This is nothing but 1 mm. So this is 41.67 millimeter. For the second case, the slit width is 41.67 mm. Now see for the third case, where lambda 3 is, see third case, we simply solve by substituting that lambda 3 here. In third case, that lambda 3 is 0.500 nanometer, that is 0.500 into 10 raised to minus 9 meter. We substitute here A is equal to 2.500 into 10 raised to minus 9. Capital D is 2.5. And again our WC is 6 into 10 raised to minus 3. See here, very simple part. This 0.5 into 2 is 1. So this is 2.5 into 10 raised to minus 9 divided by 6 into 10 raised to minus 3. 2.5 into 10 raised to minus 9 divided by 6 into 10 raised to minus 3. That is 2.5 upon 6. Multiplied by minus 9 plus 3, 10 raised to minus 6, 10 raised to minus 6, and we know that ratio is 0.4167, 0.4167 into 10 raised to minus 6. Actually this is in meter, or we write this as 4.167 into 10 raised to minus 7 meter, or we write this as 4.167 into 10 raised to minus 4 into 10 raised to minus 3 meter. We just split this minus 7 as 10 raised to minus 4 into 10 raised to minus 3, but this is nothing but 1 mm. So this answer is 4.167 into 10 raised to minus 4 millimeter. So these are the slit widths for the different wavelengths. Okay students, we stop here. Thank you.